plus or minus y would be what? 25 sine squared t. This is one way to do it. But remember that you are taking the tangent vector. So the r is xyz. And you want to look at point where 3, 4, 2 is, right? That means z is positive. So the part, the parameterization near 3, 4, 2 would be what? You just take positive part of that. So curve of intersection near 3, 4, 2 is what? 5 cosine t, 5 sine t, and then take positive 20 minus 25 sine squared t. This is one way to do it, but remember the tangent vector is what? The tangent vector is r prime, isn't it? So that means you have to take derivative, and then you have to plug 3, 4, 2. But the problem is for what value of t this is going to be 3, 4, 2. Do you see that's the problem? So that means if you want to find t, so 3 is going to be 5 cosine t, right? Then cosine t is going to be 3k. So it's getting more complicated. T would be cosine inverse 3. You still can do it, but it will be long. So I would probably, give you a alternative parameterization. Okay, alternative parameterization means you just write in terms of x. So you can write this is like x is x. So y would be what? Y is plus minus 25 minus x squared, right? X is x and z is plus minus 20 minus y squared, right? But y squared is already 25 minus x squared, right? Isn't it? I'm writing it one more time. 20 minus y squared, and this is 20. Y squared is 25 minus x squared. So that means it's plus minus x squared minus 5, right? So, but again, you are taking the positive parameterization because at near the point, all coordinates are positive. So, the alternative parameterization would be, so t 25 minus t squared, then square root of t squared minus 5. And clearly you can see at what point this is going to be 3. So clearly at r at 3, this is going to be 3, 4, 2. Isn't it? This is plus t equals 3. This is 25 minus t is 9, 16 square root of 16 is 4. Then t is 3, 9 minus 5 is 4, square root of 4 is 2. So for this problem, this is a better parameterization near the point 3, 4, 2. This is not the whole curve, but near the point 3, 4, 2. Then you can do r prime. If you do r prime, that's a tangent vector, right? So r prime will be what? 1, and you take derivative of that. You have to do chain rule, right? So 2, 25 minus t squared, and negative 2t. similarly 2 t squared minus 5 2t. If you do derivative with chain rule, you can cancel this 2. Now you plug the value 3, right? So then you plug r prime at 3. You should be able to finish it. Is there any question? If you do the other way, you'll get the same answer. Then your t is cosine inverse t first.
I have a question real quick.
Mm-hmm.
Where did the 1 come from when you took the derivative? How did you get that?
Derivative of t is 1.
Oh, okay. Right.
Any other questions? Remember one thing, for this problem we did not need the whole parameterization. We just need the parameterization near this point. That's why nothing is problem. But if you really have to find the curve of intersection parameterization of that, then you have to do normal way. If you do cosine sine t, there will be 2 parts of the curve. Alright then, let's move on. So I'll talk about the theory of next 2 sections today, 13.5 and 13.3. Okay, so let's talk about motion in 3 space. So these are the application part. This is theory wise nothing new. So first I'll do 13.5. Motion in 3 space. 3 space means 3-dimensional space. Okay. So draw the picture. You know a 3-dimensional curve is given by a vector valued function, right? So suppose the curve of a curve or trajectory path or trajectory of a moving object in 3-dimensional space or 3 space is given by the vector valued function R of t. That means what? R of t, t is the time, and R of t means the position vector of the point at time t. That is, R of t is the position vector of the object at time t. So if you draw a figure like this is the R. So at time at maybe I'll do this. At time t, so this is R of t. That means it's giving you the position vector of this point, right? And you know that velocity would be rate of change of the position, right? So which is position is given by r, so velocity would be, right, v of t is going to be just derivative of r, because derivative means rate of change. So rate of change of the position, that's your velocity. And what will be acceleration? Acceleration is, let's say, a of t is rate of change of velocity. When you take second derivative, r prime of primes. Okay. Now you know there's a difference between velocity and speed. So velocity is an instantaneous thing, and it is a vector because it has a direction. A speed is just a number, right? So speed is just the magnitude of velocity at time. In other words, just magnitude of velocity. Okay. All right. So what I was gonna say. So let's talk about the normal vector, tangent vector and normal vector, right? So if you look at this point, and okay, let me talk differently. So what is normal vector? So you know the tangent vector, right? What is tangent vector? R prime divided by magnitude. That's tangent vector, right? So R prime is tangent vector. This is unit tangent vector. So what is normal vector? Normal vector is perpendicular to the tangent vector, right? So you need normal vector. N of t, which is the derivative of the tangent vector, evaluated and is magnitude. Okay, so that means that unit tangent vector is like this. I mean, this is not tangent vector. This is tangent vector, unit tangent vector. Okay, and normal vector is perpendicular to that. This is normal vector. They're perpendicular. And why is that perpendicular, by the way? Why t and t prime are perpendicular? So I can give you the like quick. So if you do t dot t is going to be what? Length of t squared, right? but this is the unit tangent vector, so the length is 1, so this is 1 squared equals 1. Okay, now if you take derivative of both sides, the derivative of 1 is 0, so I'm writing that on the left hand side. Now let's do rule of dot product, so it's t prime dot t plus t dot t prime. But those are the same thing because dot product is commutative, so this is just 2 t dot t prime. So that is 0. That means what? T dot t prime is 0. So that means they are perpendicular. T perpendicular to t prime. Actually, this is true for any unit vector. Any unit vector is perpendicular to its derivative. That is the derivation. Okay. Any questions so far? Okay, so there another thing people talk about it. I don't think it's super important, but it's good to know. When you have acceleration, you want to know the tangential and normal direction of the acceleration. So, so let's talk about that. Suppose you have acceleration. Suppose this is your curve, and at this point, you're accelerating this way. This is your acceleration. Okay. Now you want to write this in terms of the tangent vector, which is this way, and normal vector. Let's say this is this way. I mean, they should have the same length vector. This is the tangent normal vector, unit normal vector, and this is the unit tangent vector. So if you have acceleration at a point, you want to write as a component of in terms of tangent vector and normal vector. So if you do projection, it will be like this. Okay, and if you do projection this, it will be like this. So that means this vector plus this vector is going to be A. So we write the length of this vector as AT. That means the tangential component of the acceleration, and normal component of acceleration as AN. So basically you are going to write this as AT times the unit tangent vector, AN times the unit normal vector. And how do you find AT and AN? I mean, I can give you the answer quickly. So if you take dot product with T, so A dot T would be what? AT T dot T and AN N dot T. So this is 0 because they're perpendicular. And this is just 1 because this is length of T squared, which is 1. So that means AT is just A dot T. Similarly, AN is going to be A dot N. But there is a better like formula, so I'm not going to explain that, but I'm just going to give you in terms of R. So this AT is going to be R prime dot R double prime divided by magnitude of R prime. And this AN is going to be R prime cross R double prime, take the length of that and divide by length of r prime. So this is not in your book, probably. The first part is in your book, but the second part is not. So the book only talks about this and make a complicated example. But this is also true. So I'm not giving you the derivation, but this is true. You can use as a formula. Okay. So let's do a problem. So suppose a particle moves um, with position vector r of t, which is p squared, p squared, p cubed. Okay. So you can find all sort of things. Find the velocity vector, acceleration vector, and decompose a as tangent, um, tangent and normal. Okay. So you know that this is r. So v of t is just velocity vector is, and maybe you can add this. You find the velocity at 1 and t equals 1, and acceleration at t equals 1. So this is r prime as velocity vector. 2t, 2t, 2t squared, right? And what is acceleration? Acceleration is r double prime. That's acceleration vector. Is the derivative again, 2t 60. Okay. So now at time t, equals 1, what is the velocity vector? That's v evaluated at 1, which is just 2, 2, 3. Acceleration vector, a evaluated at 1, which is the 2, 2, 6. So what is the speed, by the way? Speed is the absolute, the magnitude of v at 1, right? So square root of 4 plus 4 plus 9. So 16, what is this? 16 plus 16, 32, square root of 41, right? Whatever the unit is. So this is uh, distance per time squared, right? I mean time. This is the unit. This is the velocity. I mean speed. Velocity is a vector. Speed is just a number. Okay. Now at time t equals 1, also you wanna. Okay. So this is the tangent acceleration vector at t equals 1. Now you want to write in terms of tangent vector and normal vector. So what is unit tangent vector, by the way? Unit tangent vector is r prime divided by its magnitude. So we can do at 1. So let's do at 1. Tangent vector at 1. That's what we are trying to do. So if you do r prime at 1, r prime is this. So this is 2, 2, 3. And then length of 2, 2, 3. We already kind of done the work. This tangent vector. What is normal vector? Then we have to take derivative of the tangent vector. So we should have done the work for t. Because you know what I'm saying? The normal vector is what? The tangent vector prime over its magnitude, right? So we have to find t as a function of t. So let me just delete some of these. So what is tangent vector? R prime t divided by. So R prime you already know. 2 t 2 t t squared. And square root of this. So 4t squared plus 4t squared plus 9t to the 4. Right? So it becomes 1 over square root of 8t squared plus 9t to the 4. 2t, 2t, 2t squared. This calculation is going to be long. So what is normal vector? You need normal vector. The normal vector is t prime over its magnitude, right? So what is t prime? You have to take derivative of this, right? So actually, I don't know. Hold on. If I just know these, I really don't have to work on this. You see what I'm talking about? I already know this part. So that means I already know this part at 1. So the other part would be this minus this. Okay? So that's probably easier way to find normal vector. That's your book does also the similar way. Okay? But you need to find AT. That's the part. So let's find AT first. So sorry, this is a little bit disorganized. So let's find, we find T, but let's find AT. So remember what AT is. AT is AT at 1. R prime at 1 dot R double prime at 1 divided by R prime at 1. Or you can do the other way. The other way is if you do A dot It is similarly, it is a dot t. That's also the other way to do that. I don't know which one is easier. We already find a, right? What is a? A at 1 is 226, right? And we already know t of 1 is this. So if you take dot product, that would be your AT. That's another way to do it. So let's do dot product. 226, okay? And dot with t at 1, which is 23. If you dot it, what do you get? 4 plus 4 plus 18, right? So 26. Is that right? I think I made a mistake. 9 plus 4 plus 4, right? 8 plus 9 is what? That's not right. Is this the, what is the magnitude of that? 4 plus 4 plus 9, isn't
It
it?
should be 17.
Yeah, it should be 17. I keep writing it wrong. Sorry, 17. Sorry. Okay, so this is the AT, and already we have T, right? T upon is already this. So look at this. I'm gonna use this. So if you write A at 1, this, right? I already know A of 1 is 2 to 6, right? And we just find it, AT at 1 is 26 over square root of 17. And T of 1 is 2 to 3. Then the rest is AN, right? So that means what? I just subtract this, then that will give you AN. So if you do that, AN is 226 minus 26 over 17, 2 to 3, right? If you take 117 as a common factor, this is 17 over 17, right? Then we take 1 over 17 as a common factor, then this is 34, 34, and what is 6 times 17? 102, is that right? Minus 52, 52, and 3 times 26 would be 78. So take 1 over 17 as a common factor, 34 minus 52, 18, negative 18, negative 18, and 24. So that's the normal component of the vector. But if you do want to find normal vector, then you just divide by its length. So if you take um, so remember, if you do that, this is just n and normal vector length. The normal vector is 1. This is just n. So if you take length of this, that becomes your n. So I'll let you do that. I think the answer is going to be 6 square root of over square root of 17. Then the normal vector is you just divide this by this number. So so if you look at this one, so normal vector is what? N normal vector divided by n. So I already know a and n. So this is 1 over 17, negative 18, negative 18, 24. And we already know n, which is 6 square root of 2 over square root of 17. If you do all the work, it's going to be 6 square root of 2 times square root of 17. This is the normal vector at 1. This is all at 1. Any questions? Okay, so let me just mention about the arc length one. The next, I'll probably discuss again next time. So this is 13.3 arc length. This is also an like application, nothing else. So if you have a space curve and you want to find the length, there is an example. And let's say you have an helix. Helix starts from 1, 0, 0, and then stop here. So you go from 1, 0, 0, and this point is 1, 0, 2, 5. The helix is given by parametric equation that cosine t sine t and so find the arc length of the helix from the point 100 to 1025. Is the problem clear? How do you find the arc length if the equation is given? So first of all, you need to know at what value of t you get this point. You see, you get this point at what point? When t is 0, right? So, so r at 0 is going to be 100. And it is clear, I mean, when t is 2 pi, then so r at 2 pi is going to be 102. So these 2 points corresponds to, you know, this point and this point for t equals 0 and this point for t equals 2 pi. That's the parametric value, the parameter value t. Okay, so what's the formula? So I'm just going to give you the formula. So this is, I'm not talking about the, um, I'm not going to give you the derivation of the formula, but this is the arc length formula. The arc length is going to be from 0 to 2 pi, and then magnitude of r prime. That's the formula. So if you do this, 0 to 2 pi, and what is r prime? If you take derivative of cosine is negative sine, derivative of sine is cosine, and derivative of t is 1. Okay. So now if you do the magnitude formula, that will be sine square t plus cosine square t plus 1 square t. Sine square is cosine square is 1. This is 1. So this is basically becomes square root of 2. Then you square root of 2t from 0 to 2 pi. And if you do that, this will be square root of 2 times 2 pi. So yeah, right. That's the arc length from this point to this point. So another version people do write this problem. If you write r as like x, y, z, then r prime is x prime, y prime, z prime, right? And if you take its magnitude, it becomes square root of x prime squared plus y prime squared plus z prime squared. So another arc length formula is from a to b is a to b r prime t dt, or if you write in terms of x, y, z, a to b square root of x prime squared plus y prime squared plus z prime squared dt. So I'll upload problem set on these two sections. they're basically small application of what we have done. This is nothing new. Okay. Any last minute question? So I'll upload the problem set. It's very small problem set. It is going to be 3-4 problems, and then you can talk about it and present it tomorrow. And then what's the plan? We are going to do chapter 13 review on Thursday, and the exam 1 review on Tuesday, next week Tuesday, and then you'll have exam 1 on Wednesday. Any last minute questions? All right, so I'll upload the problem set. You start working on it. So tomorrow will be just talking about the problems. You present the problems. Okay, they are not going to be hard because it's simple few formulas, right? They're taking derivative, taking integral. All right, guys, I'll see you tomorrow.